Hello, welcome back to lecture 13 of our course on advanced quantum mechanics. Here is where we are in the course. We start with the Hamiltonian, then we derive the equations of motion, the canonical commutation relations, and hermiticity conditions. And when we solve all of these, we obtain the x hat of t and the p hat of t. Let me drop the indices. It's implied that these can have indices. And any polynomial of those, f hat of t. Once we have these, we can then use or choose a state vector, initial state vector in a Hilbert space, and then we obtain x bar of t as psi x hat of t, psi, and p bar of t. Similarly, and these now are numbers. So now we can make all sorts of predictions. We have all the ingredients. However, in practice, we do these steps in a basis. Almost always. In practice, use a basis, actually a Hilbert basis, for these steps. It's not so convenient generally to work with the abstract operators and the abstract Hilbert space vectors, even though they are describing the physics directly. Mathematically, they're a little cumbersome to use. So in practice, we use a basis. E.g., choose a Hilbert basis of vectors that we may want to call Bn vectors, where the index n ranges over some integers, maybe all positive integers, or all integers, etc. You don't have to specify that at this point. And then we can use this basis to write down a resolution of the identity, sum over n, Bn, Bn, so that then what we had written above, for example, these abstract equations that contain no numbers whatsoever, they contain here, these expressions contain only a vector in the Hilbert space and an operator on the Hilbert space, but no numbers. So we can turn these expressions here, these matrix elements, they're also called matrix elements, we can turn them into explicit expressions where we have actual matrices, actual vectors with components to work with. So, so that, for example, f hat of t equal to psi f, sorry, this is f bar of t, of course, it's the prediction. So f bar of t, f hat of t psi, can also be written as psi identity and then f hat of t identity psi. And we use these resolutions of the identity here, and then we have that this is psi. Here we have a sum over n and m. And we have psi and Bn. Bn, f hat, and then Bm, Bm psi. Now this is called Bm, psi m. This here is the complex conjugate of psi n. So this is psi n complex conjugated because the b is on the right, not on the left. And here, this we may call the matrix element. This is the nth matrix element of the operator f hat in the B basis. And of course, there's a t of t here. So therefore, we can write down this abstract thing here that has only vectors and operators in it. We can write this instead in terms of things that are just numbers. Everything is a number in this now, which is sum over psi star n f hat of t n m and then psi n. See, everything is numbers here. And that's good because that means we can do summation tools, or because we can also do this in a continuous basis, integration tools and differential equations and integral equations, and all of these tools become available once we choose a basis. Indeed, continuous basis also, there exist continuous basis. Now, I want to be very careful in these things. If you want to learn about quantum information, quantum field theory, or quantum gravity, or really any advanced topic in quantum theory, then this business with the bases is super important. It's super important that you completely understand how that works, how you go from one kind of basis to another kind of basis, to a basis-independent formulation, and back to a basis. This needs to be completely natural. And there are some subtleties in there. Subtleties that are sometimes, or quite often actually, not mentioned. But they do come up in research. And they're super cool. They have to do with quantum gravity and all sorts of interesting things. And therefore, in this course, I do that quite carefully for another 1.5 lectures. And then we get to some of the cool stuff to do with the subtleties with the bases and observables. And then we move on to things that have nothing to do with bases anymore. I mean, then I will just take it for granted that we can easily flip between bases. But for now, let's just do this super carefully to make sure that you are all super familiar with choices of bases. Okay, so there exist continuous bases, and let's call them, for example, a basis of vectors C with an index that we may call lambda. And let's say that this index set is running over all lambdas in a set, in an index set J. So this is some continuous set. For example, an interval on the real line, or maybe 27 continuous intervals on the real line, or the entire real line. So then what we have is a structure that's completely analogous to what we had for the sums. We can again write down a resolution of the identity, but we now have to integrate over the index set instead of summing over the index set. And we have these basis vectors C lambda, and then D lambda. I mentioned already that these C lambda are technically not in the Hilbert space, but they are approximate eigenvectors. And we had that already when we discussed last time the continuous spectrum, that there are no proper eigenvectors, but they're improper eigenvectors, approximate eigenvectors, which is to say you can always find a sequence of Hilbert space vectors that get arbitrarily close to being an eigenvector to the given eigenvalue. All right, but I don't want to review all we did last time. So once we have this resolution of the identity, we can do what we did with the resolution of the identity up here. We can write down operators in a basis. So we can then write, in particular, the expectation value that we calculated above, which is psi f hat of t psi. And now instead of choosing a discrete basis, we choose this continuous basis. So we say this is psi identity. Oh, we don't need that bar. F hat of t identity psi. And this is now the integral, in fact, double integral, because we have two resolutions of the identity. Integration over the index set, the continuous index set of lambda. And then we have psi, c lambda, and then c lambda, f hat of t, c lambda tilde, c lambda tilde, and psi, and d lambda tilde. Let's identify what we have here. We have here psi index lambda tilde, and here we have complex conjugate of this. So we have psi index lambda, but complex conjugated because the psi is on the left, the c is on the right. And when you flip such an overlap, then the inner product of a Hilbert space is such that you pick up a complex conjugation. And this here is now, again, what would be a matrix element if the lambda were discrete, but they are not. So let's write here lambda and lambda tilde. Now, this would be the natural way to write it, but actually in the literature, the notation is a little different. Namely, we write here psi of lambda star. So this is this. Just a name. I mean, it's just for every label we get a number. It's the same as a function. And then here we write f hat of t and of lambda and of lambda tilde. And from here, this is this. And from here we have psi of lambda tilde, and then we do d lambda tilde. So you see, again, up here, everything here is abstract. A vector in a Hilbert space, an operator in a Hilbert space, no numbers in this expression. Here, on the other hand, it's all numbers, all number-valued functions. This is the kind of thing that we have mathematical tools for. That's why we choose bases. Also, notice there exist mixed bases, as we will discuss today in a little bit more detail. So in principle, this is all good and fine, but where do we get these bases from? Is there a method to generate bases? So what bases to choose? Are there natural choices? Well, it turns out that yes, there are natural choices for bases. Namely, notice we have that every self-adjoint observable f hat possesses a so-called eigenbases. You know, this word here, eigen, you may wonder, what does that mean? Well, it's a German word and it means own. it means it's the own basis of f hat. It's the basis that belongs to f hat. So it's its own basis. All right, so possesses an eigenbasis. And the eigenbasis may be called the basis of vectors f with an index mu. And this mu could run through a discrete or continuous index set. Mu can be from a discrete and or continuous index set. And that's very important. This is the content of the spectral theorem that we will cover today. And what it means is that these bases are typically very useful to employ when an observable f hat is important in a particular calculation. Let's say you want to know something about the energy of a system. Well, then it may be convenient to use the Hamiltonian's eigenbasis, the basis that belongs to the Hamiltonian. And similarly, if you want to work with angular momenta, then maybe you choose an angular momentum eigenbasis, or if you're interested in where a particle is, then you use a position eigenbasis. The spectral theorem guarantees that these eigenbases do exist. So, question, how do we know these f hat possess eigenbases? And the answer is, this is the content of the spectral theorem. Oh, just a sec. This is the spectral theorem for self-adjoint operators. Now, in order to be able to discuss the spectral theorem, we had to first clarify in the previous lecture what does self-adjoint mean, and what does the spectrum mean. Let me quickly remind you of the key points here. So what we have is that self-adjoint means that f hat acts the same way that f hat dagger acts on whatever vectors both are defined, and this is important, the domain on which f hat can act has to be the same as the domain on which f hat dagger acts. Again, sounds like a subtlety that might as well be overlooked, but actually there's very interesting physics in this, as we will see later in this course. All right, so we defined what self-adjointness means. And remember, self-adjointness is having a non-trivial issue here only in infinite dimensional Hilbert spaces. In finite dimensional Hilbert spaces, in other words, in the linear algebra of complex vector spaces, self-adjointness is a very simple thing. But in infinite dimensions, it's more complicated, and I will illustrate the definition and the loopholes and the interesting examples later in this course. We also discussed what the spectrum means. What does the notion of spectrum mean? Well, remember, recall the spectrum of an operator Q hat, where Q hat is an arbitrary operator. I'm using the letter Q hat instead of F hat because F hat is usually reserved for observables. But Q hat doesn't have to be self-adjoint or anything like that. It could be just any operator. And the definition of the spectrum for just any operator on a Hilbert space is given by this definition. A number Q in among the complex numbers is an element of the spectrum of our operator Q hat if, so it's the set of all Q in C such that the operator Q hat minus little q times the identity does not possess an inverse, does not possess an inverse on the Hilbert space. This was the definition. And what was important about this is that this definition achieves something important. We can talk about intuitively about what eigenvalues are without having to talk about eigenvectors in this way. That was the key, why this is a good definition. And we saw that the spectrum of an operator, of a linear algebra, of a linear operator on our Hilbert space can be decomposed into a point spectrum of Q hat that consists of isolated points, isolated eigenvalues that correspond to eigenvectors, or that have eigenvectors, and a so-called continuous spectrum, continuous of Q hat, and a so-called residual spectrum, residual of Q hat. Now this here corresponds to eigenvectors in the Hilbert space, and then here only approximate eigenvalues. So the elements of the point spectrum we call eigenvalues. The elements of the continuous spectrum we call approximate eigenvalues with approximate eigenvectors. And for now, we have to say, well, they're not in the Hilbert space. What the deal is with these approximate eigenvectors, we will see later. And the residual spectrum is empty. It has no elements for self-adjoint and unitary operators. So we will generally not worry about the residual spectrum. But it's good to keep that in mind, that it exists in principle, because in quantum theory, we do not only have self-adjoint and unitary operators. Other operators do occur. For example, remember those A and A dagger operators that we had before? They're not self-adjoint. They're not unitary either. Okay. We are ready for the spectral theorem now. Let's start it on a fresh page. The spectral theorem. Wow. Spectral theorem for self-adjoint operators. There's also a spectral theorem for unitary operators, and the most general spectral theorem is for so-called normal operators. I will mention that later on in a bit more detail. Normal operators are operators that commute with themselves. Self-adjoint operators, that commute with their adjoint. Unitaries commute with their adjoint. Self-adjoint operators commute with their adjoint, and other operators may or may not commute with their adjoint. If they do, then they can be diagonalized. Okay, so the spectral theorem for self-adjoint operators says the following. Assume f hat is self-adjoint operator, i.e. F hat acts the same way as f hat dagger on the vectors that they are defined on, and we also must have that the domain of f hat is equal to the domain of f hat dagger. Right, so let's assume that we are dealing here with a properly self-adjoint operator. Then we have that the spectrum of f hat is a subset of the real numbers, or indeed it could also be all of the real numbers. And as I mentioned before, the residual spectrum of f hat is the empty set. And f hat possesses an eigenbasis, and we will have to refine that notion, but I didn't want to wait with the spectral theorem until we can do this. An eigenbasis of eigenvectors, and I'm putting this in quotation marks because some of these may be proper eigenvectors and some may be improper ones. That is to say, some may be vectors in the Hilbert space and others may not be. So the ones in the Hilbert space will be called eigenvectors, and the ones that are not in the Hilbert space will be called approximate eigenvectors. Consisting of eigenvectors in H and or approximate eigenvectors that are not in H, which correspond to the point spectrum of f hat and the continuous spectrum of f hat respectively. Which is to say that the proper eigenvectors correspond to proper eigenvalues, which are by definition part of the so-called point spectrum. And then there are also the improper or approximate eigenvectors that are not in the Hilbert space, which correspond to improper eigenvalues that are in the continuous spectrum. Let's look at this, starting with a very simple special case. So, simple special case. Dimension of the Hilbert space is finite. Say capital N. Well, we notice in finite dimensional Hilbert spaces, all vectors are normalizable, trivially, because they all have finite length. And therefore, if we combine that fact with the spectral theorem, we can conclude that the spectrum of an self-adjoint operator, f hat, in this case, is equal to the point spectrum. Because there cannot be any non-normalizable eigenvectors. There cannot be any improper or approximate eigenvectors. And so there cannot be any improper or approximate eigenvalues. Everything has to be point spectrum. So the bases, bases are countable in these Hilbert spaces. In fact, they're finite, and we have, actually, I should not write f here because as far as we know so far in our course, the f hat are observables that live in an infinite dimensional Hilbert space. So let's say that we have q hat is equal to q hat dagger, right? So then the basis might be called the basis of eigenvectors Qn, n equal 1 to capital N. We must have as many basis vectors as there are dimensions in the Hilbert space, of course. So we have q hat Qn equal to Qn, Qn. We have that the identity can be expanded as Qn, Qn. And therefore, we can write, for example, the matrix elements Qm, Q hat, Qm. So we are writing our operator, self-adjoint operator Q hat, in its own eigenbasis. And then we find that this is, well, Q hat acting on Qm, that gives us a Qm, right? So this is then Qm, the number, times Qn, the vector, Qm, the vector, which is Qm delta Nm. And therefore, we have that Q hat is diagonal in its own basis, in its eigenbasis, right? Because we have that Q hat Nm, this is this, this is Q hat NM, is equal to this matrix, Q1, Q2, etc., and the rest is 0. All right, so if we take a self-adjoint operator, then in its own basis, it is diagonal. Now, this was in finite dimensions. Let's see how this all pans out for self-adjoint operators in infinite dimensional Hilbert spaces. Now, assume that the dimension of our Hilbert space is actually infinite. Now, case one. Case one is that the spectrum of our observable f hat is the point spectrum. So it has only proper eigenvalues and proper eigenvectors. Example. An example would be f hat equal to p hat squared over 2m plus k half x hat squared. This is, of course, the Hamiltonian of the harmonic oscillator. And it turns out that, well, we know the harmonic oscillator's energy spectrum is discrete. And yeah, that means that the eigenvalues of this operator are in the point spectrum, and all the eigenvectors are normalizable. That would be an example here. So in this case, we have that f hat acting on the set of eigenvectors is equal to fn, the number, fn. And so we have a basis of f hat n basis vectors. That's a Hilbert basis, which means in particular that we have that the fn are orthogonal to the fm. We can write down a resolution of the identity, sum over n, and then fn. And we find, as we did in finite dimensions, of course, that if we look at our abstract operator f hat in its own basis, in its eigenbasis, then this is, of course, fm, so this is fm, fm equal to fm delta nm. So again, of course, an observable whose spectrum is a point spectrum can be written in its own basis as a matrix which is diagonal, namely f hat nm is f1, f2, f3, etc., and zeros everywhere else. It's diagonal. Okay, so far so good. Oh, yes, we also want to write, of course, wave function. So we have psi equal to identity psi. But the identity can be written in terms of the basis that we chose. So we can write this as the sum over all n. And then we insert the resolution of the identity fn, and apply this to psi. We recognize this is psi n. That is the wave function of the state psi in the f eigenbasis. So this is the sum over n, psi n, fn. here, Fn, the set of the Fn is called the wave function. Oh, sorry. It's of course the psi n. The psi n, the set of the psi n is called the wave function of the state psi in the eigenbasis of the observable f hat. Also, we can express now operators in the eigenbasis of f hat. So, operators in the eigenbasis of f hat. So take, for example, an operator g hat. And we want to express it in the eigenbasis of f hat. Well, we write it as the identity to the left, g hat, and then the identity to the right. We can write this as the sum over n and m, and then resolution of the identity, fn, g hat, fm, fm. These are the matrix elements of g hat in the basis of the f hat. Sum n, m, and then g hat and m. Remember, these guys are just complex numbers. And then here we have fn, fn. Any operator, forgot something, this is an m here. Any operator in Hilbert space can be written in this form. Just like a vector can be expanded in a basis, any operator can be expanded in a basis as well, and then it takes this form: a basis vector ket, a basis vector bra, and then complex coefficients in front. You can start with your abstract operator coming from some abstract considerations, insert a basis left and right and get this, but you can also invent or specify your own abstract operators by starting in this way. You write down the ket and bra of some basis of your choosing, and then complex coefficients in front of it, sum the whole thing up. What you get is a linear operator. And this here, these numbers here are called the matrix elements of g hat in the eigenbasis of the observable f hat. Let us use this to do a little exercise where we start with an abstract equation. So exercise, rewrite abstract equation, an equation like phi equal to g hat psi, whatever the psi and the phi might be. We might encounter an equation like this at some point. And the exercise consists of rewriting that abstract equation in the f hat eigenbases. So solution, well, what are we going to do? This is a vector equation. Let's make it an equation for numbers by multiplying from the left with the basis vectors, first of all. Then what do we obtain? So we obtain fn phi equal to Fn g hat psi. That's already nice because we have now only numbers in this equation. On the left-hand side, we have here the phi n, the wave function of phi in the bases and the eigenbases of f. On the right-hand side is also a number altogether, but it's still a matrix element. So what we can do is, we can write this with an identity in here, and then it becomes sum over m Fn g hat, and now we insert the resolution of the identity Fm psi. Now, this is a number, just the matrix element again, and this is psi m, right? So this is g hat and m numbers. So overall, what we have is phi n equal to sum over m, and then it's g hat n m, that's a matrix, and then psi m. So really what we have is column vector, matrix, column vector. So this here is the concrete basis dependent version of this abstract basis independent version of the same equation. So this already expresses all the physics, and that's nice because it's a statement that's basis independent, but this one is practical. This is the kind of thing that you can feed to a computer, you know, working with coefficient numbers. Now, case 2. Case 2 of the spectral theorem. Case 1 was that we had only a point spectrum. Now, case 2 is that the spectrum of our observable f hat is equal to the continuous spectrum. Continuous spectrum of f hat. So there is no point spectrum. And examples will be, and we get to that later in more detail, when you choose f hat is equal to x hat, the position operator, or you choose f hat to be the momentum operator, or you choose f hat to be the momentum operator squared divided by 2m. In each of these cases, we have that there's no point spectrum, there's only a continuous spectrum. For the position operator, the continuous spectrum would be the real line. For the momentum operator, the continuous spectrum would also be the real line. For p squared over 2m, the spectrum would be what? Not the real line, it's only the positive real line, because p squared is a positive operator. But again, it's just a continuous spectrum. There is no point spectrum. There are no normalizable eigenvectors here. In general, let us call the spectrum, in general, call it J, just so that we don't have to write spec cont of f hat all the time. So J will be the continuous spectrum of our operator, and it could be some interval in the real line, or it could be consisting of 2 intervals, or any number of intervals in the real line, or it could be even half axis or the entire real line. So this is a subset of our continuous subset of R. Now the notation that we will use is this. Notation to use is we write f hat acting on f equal to f. You see, we could write here instead for the basis vectors, we could write b index f, where f is the eigenvalue, right? We could do this, but nobody does that in the literature. instead, in the case of continuous spaces, we usually, not always, but usually label the basis vectors simply by the eigenvalue. Okay, so this is, for example, if we have discrete basis vectors, then we usually write this. But sometimes we would also just write this, where the index is the name of the basis vectors. This can be a little bit confusing if you have several discrete bases around, right? That's why it's better to give these things names. But in the continuous case, this is a fairly common practice. So that, for example, for position eigenvectors, we would just put an x in here, or momentum eigenvectors, we put an x, a p in there. Okay, so our notation will be this for continuous spectrum. Okay, so we have this, and then we have, and we will address the exact meaning of this later on. We will have continuums normalization, namely that they are not orthogonal in the same sense that normalizable vectors can be orthogonal. Now, this is a Dirac delta instead of a Kronecker delta. So this is Dirac delta function. Well, and we can resolve the identity operator again in terms of this eigenbasis. The spectral theorem guarantees us that we can do this. And the range of the integration is over J. I don't know why the software does this extra hook there. I don't know why it does that. Okay, so we have this df. And now we can repeat the same calculations that we did for discrete bases for the continuous bases too. So now we obtain that psi is equal to the identity psi, and using this resolution of the identity now, we obtain that this is the integral over the interval or intervals j of f psi df. And this is psi of f. And so we can write this as the integral j of psi of f, and then f df. Here, this is the wave function of the abstract vector psi in the eigenbasis of the operator f hat. So what we've achieved is we have expressed an abstract Hilbert space vector in terms of a concrete function by choosing a basis. And just like we did in the case of a point spectrum only, we can do the same thing for an operator. Namely, we can also start with an abstract Hilbert space operator G and express it in terms of the bases. So now this becomes integral j, and then we have the resolutions of the identity, which are f g hat, and f tilde, and then df tilde. This we would still call matrix elements of G hat in eigenbases of F hat. And we would write this as G hat of F and F tilde. So we write it as a function in the matrix case, when we had a discrete set of basis vectors, we would use f and f tilde as indices here. But in the continuous case, we like to write it as an argument. But we could also write it as g hat f f tilde, right? Just to make the similarity to a matrix clearer. You see, we can't write this down as a matrix because the label is continuous, but it plays the same role as a matrix does. However, since this is not really a matrix and we are not summing, we are integrating, there is another name that is also used here. Terminology. Namely, we say that g hat of, no, not lambda, we have f's here. G hat of f and f tilde is an integral kernel. Okay, so an operator in a Hilbert space, when expressed in a continuous basis, is called an integral kernel. That's the continuous version of what a matrix is. And remember that whether we're dealing with a matrix or an integral kernel has nothing to do with the operator. It has everything to do with the choice of basis that we use. The same Hilbert space operator can always be written as this matrix or that matrix or another matrix when you choose this discrete basis or that discrete basis or that discrete basis, but it could also be written as an integral kernel, right? So it's not a property of the operator, whether it's an integral kernel or a matrix. It's a property of your choice of basis, whether it appears one way or the other. Remember, when we were dealing with the discrete basis, we did an exercise. Rewrite the abstract equation, which was phi equal to some abstract operator acting on some abstract Hilbert space vector in the basis. So how does this look like now? Well, we have this, and let's apply, first of all, a basis vector from the left so that we get a number-valued equation. So then we get f is some eigenvector of our operator f hat, phi, is equal to f g hat psi. And as we did before, we put the resolution of the identity here. Then, I think it's best to do this one line below. Then we obtain that this is the integral over j of f g hat, and then the basis f tilde and psi and d f tilde. That was our resolution of the identity in terms of the f tildes. You see, the f and the f tilde are the same vectors. I just used a different variable to denote them so that it doesn't clash with the f that we put on the left here. And what are these things now? This is the integral kernel of g hat in the f basis. So this is g hat of f and f tilde. And this is the wave function of psi in the f tilde basis. And so overall, we have, since this is the wave function of the state phi in the f basis, so we obtain that phi of f is equal to integral j and then g hat of f and f tilde psi of f tilde d f tilde. There we go. This is the concrete basis-dependent version of this abstract base, oh, no, not this one. Further up, it is this here is the abstract version. And down here we have the explicit version in a basis. So you see, in a basis, it's usually more cumbersome, but we can employ our techniques for integrating and differentiating and whatnot, whereas in the abstract level, things are simpler, but sometimes not as explicit. Well, and then we have case 3. Case 3 in our spectral theorem for self-adjoint operators, and that's the case where the spectrum of our self-adjoint observable is equal to, well, a point spectrum, F hat, but also a continuous spectrum. And both are non-empty, both non-empty. So the spectrum has both continuous stretches and discrete points. What would be examples? Atoms, just a sec. The Hamiltonians. The Hamiltonians of all atoms and molecules. They're always like that. Well, then, how does our basis look like? Then we have a basis which consists of a set of fn's and a set of f's, where they run continuous label here, and this is a discrete label. And they run through index sets. The f may run through one or multiple intervals on the real line, and the fn could be any number of discrete points. It could be that there is just one discrete point in the point spectrum. It could be that there are 100 or any number and infinitely many. All of that is possible. So in this case, then, we would write that the resolution of the identity then is a sum and an integral. Then we would have to sum over all of the fn, and we would have to integrate over some index set, f in j, element of j. That's what I meant to say here. F df. So we have both here. And that also means that our operator, f hat, is then, if we apply the identity left and right, hat f, and then dot, 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 I leave it to you to fill this in, then we obtain that this is the sum over n of the fn plus integral over whatever the continuous index set is, the f, and then f df. And we see that intuitively speaking, our operator in its eigenbasis is diagonal again, right? Because this has the same label as that, fn, and here the same thing. However, diagonality is, of course, really only a term that you can use for actual matrices. when the label is continuous, then diagonality is a rather non-trivial concept, and we will have to come back to that later on. Okay, so this is the generic case where case 3, where we have both a point spectrum and we have a continuous spectrum. Now you may wonder, is that all? Have we exhausted everything? Are these all cases? The answer is yes and no. Answer 1, yes, for the spectral theorem. These are all the cases covered by the spectral theorem. But there's also answer 2, which is to say, there are f hat, just a sec, there are observables f hat that are not self-adjoint. And they have cool features that we will see later on in the course. I mean, for example, I think I mentioned that example earlier, the momentum operator of a particle in a box, it's not self-adjoint, but of course you can measure the momentum there. And what that means is that the spectral theorem is evaded for a reason that we will see. And so there is no eigenbasis of the momentum operator of a particle in a box. It just isn't. Not a discrete one, not a continuous one. There is none. And that has physical implications, namely that the momentum cannot be resolved more sharply than a particular minimum amount. And that sort of behavior, that there's a minimum uncertainty in some observables, may well arise in quantum gravity as well. I will make some brief remarks about this later on. It's of course not really our main topic here, but I want to cover things to enough technical depth that you can understand these things when they come up. Okay, this is as far as we got today. See you then.